Talk about graphing. Anybody had any experience graphing? Maybe in math class? Okay. So you're familiar with the Cartesian coordinate system? Okay. Use your imagination. That's a straight line. There's another straight line. So if this is our sheet of paper and it has a grid on it, right? The lines in the paper are called the grid. We just divided that region into 4 quadrants. Right? I think the method calls it A, B, C, D, clockwise. Why would we want to do this? Well, if we have a set of data, say we have, and it works best for binary data. In other words, we've got a factor X here and a factor Y there of variables, and we control one of them. We control the X variable. We change it, and we watch what happens to the Y variable. So we got numbers, and the response. This is the independent variable because we control it. The dependent variable changes with respect to what we do over here. Okay. This line is called the abscissa. And this line is called the ordinate. Alternatively called the x-axis and the y-axis. Related to these terms, independent variable is always on the x-axis. That's the one we control. The experimenter changes these values to see what happens to the other values. Now, this point right here is called the origin. And for either line, this is the 0 point. So 0 going this way is positive, and going this way is positive. Positive values. Going this way is negative values, going this way is negative values. So if we were just to look at any one of these numbers, we could plot it on this line somewhere. All right, let's say we plot it right there, plot one there. Say we're looking at this one, we're plotting that one right here. Well, that doesn't tell us anything about what happens to the y. Because at this one, the y may be somewhere up here. So the data point that we're referencing here is a combination of the x and y values, which can be plotted in this space, in this quadrant, right there. And this would be the x and the y value, right there. Okay. All right. So this value represents a measurement. We change something, watch what happens. That's a measurement. Let's see, we've covered that already. All right, let's see. Okay. So notice for this example, we've got the data on the right-hand side. Right? Temperature is X. That's what the experimenter changes. And volume is the Y. We're talking about a gas. If we confine a gas and we maintain the same pressure on that gas and allow its volume to change, as we change the temperature, we notice that as the temperature increases, the volume increases. So we plot those values in this space. I'd say something like Maybe one here, one here, one here, one here. That's not a good example. Hold on a second. Let's start over. So if we make this temperature in units of Kelvin, then we know that for Kelvin, the temperature scale doesn't go beyond that, right? 0 is the bottom of Kelvin. So it'll never go beyond that. Okay, so if we measure temperature and its response volume in liters, then we get several points. Those are our data points. And what we can do is we can draw a best fit curve or a best fit line to those data points, because we know that each measurement is going to have some error, and the error is going to take it away from our best fit line. So we look in here and we try to minimize the deviation from the line. And so it's better if we can see through the ruler, but let's say we go maybe like something like this. Here, there. That's fair. So now we've got a best fit curve for those data points. And what we can do now is we know that if we go to this data point, we should expect that volume. Go to this temperature, expect that volume. What if we want to look at something in between, say right here? If we want to go to this temperature and see what that volume is. Right? That's not part of our data set, but now that we've got a best fit line, we can do that. We can use that line to say, what if? Everything inside that's bracketed in by this data set, that is called interpolation. Now, if we want to look at temperatures below or above that, say we want to look out here, we may assume that that line extends this way. And it probably does, but there's no guarantee because there are no data points out here to prove it. You know, it could go this way, it could go that way, for all we know. But in this region out here or here, this is extrapolation. And that's dangerous territory. You have to do that only when you have to. Okay. So if we were going to present this graph in a referee journal paper, why would we want to do that? Well, if our data set were not just these 6 data points, right? 6 X's and 6 Y's, then we would want to talk about them in such a way that we can convince our reader of our position. Our interpretation of the data is such and such, and we want the reader to believe us. So one of the ways to do that is to draw a graph, right? Humans are visual creatures. So if we see the data in this form and we talk about it as a visual representation of the experiment, then we may have a better chance of convincing them that what we say about it is correct. So if you're going to publish a graph, it needs to have certain information in it. Overall, the graph has to stand alone in the paper. Now you can read the text in your publication and reference the graph in the text, talk about it. But if somebody wants to look at that graph and make something out of it without taking your opinions into account, the graph needs to stand alone. It has to stand alone. So it's got to have a title to tell us what we're trying to do, what the graph represents. So we got the title there. We've got our axes drawn in. We've got the units of measure and the scale units. Right? We have temperature and what the temperature units are, Kelvin, or volume and what the units are, liters. then we've got them marked off in the grid in equal increments. You'll notice that on the bottom, we go 50, 100, 150, and they're 50 units each. They're the same all the way across. We don't say, well, I've got a data point here that's at 100, but I got another one over here that's 200. I want to put it here. And I got one at 300. I want to put it over here. You can't just guess it. It's got to be equal increments. At least for our purposes. So you have to know what each one of the grid units represents. How many units is it? Notice that between 50 and 100 is 5 blocks. So each one of those blocks is how far do you move? 10 units, right? 10K. So it'd be 50, 60, 70, 80, 90. The next one, next major line. So you've got major and minor lines. The next major line is 100. You go 5 more blocks, 5 minor lines, and you get to 150. Okay. And you do that for both axes. And what you want is for, ideally, for the graph to take up as much of the paper as possible. You want to spread it out so that when you go to interpret or interpolate, then you have more room to work with. You have a finer detail available to you. Now this one gave up a lot of room for the data table. If you don't have the data table there, then you can spread one of the axes out. Usually the axis with the largest spread of data gets the long axis. So in this case, that paper is in landscape mode to give the x-axis as much room as possible. And the y-axis covers less territory, less spread of numbers, so it's the shorter side. Okay. Now, I got a bone to pick. I've already mentioned this before. A bone to pick with who drew this graph. They've got orphan decimals all over the place. Right? On that 0.2, 0.4, 0.6, 0.8, it needs to be 0.2, 0.4, 0.6. Right. So I would take issue with the creator of this graph. Okay. Let's see if I missed anything. So you need to know scale units. You have to identify the scale units and how much each is worth. Draw your best fit curve. Okay. Now we can talk about the difference between a direct relationship and an inverse relationship. Everybody know what slope is? Slope of the line? Okay, rise over run. If you have a positive slope like this one, right, as temperature increases, volume increases. That's a positive slope. That's a direct relationship. If you have a line that's, say, like this, that's a negative slope. That's an inverse relationship. Okay. Or even if you have a curve like this, wherever that line is tangent to the curve, it's a negative slope, or a negative slope, or a negative slope. So that curve itself is an inverse relationship. We'll talk about preparing the graph in just a minute. I've already mentioned some things about it, but let's see. No, maybe we better do it. Just take it in order. Let me erase some of this stuff. So when you're hand drawing a graph, you've usually got a sheet of 8.5 by 11 paper. If at some point in the future you draw graphs with a computer, then it's irrelevant. Right? You can make it any size or any shape you want. But for our purposes, with a sheet of graph paper, you want to do that first thing talking about is, do you want portrait or landscape? It depends on which axis needs to cover the most ground. So that's number one. Portrait versus landscape. Right. Then you want to know the scale units. Right? Are you talking about grams or liters or atmospheres? You know, what do the units represent here? Then you want to subdivide the grid to accommodate all the data. That is, make it fit as much space as you can. And then once you've decided that, and actually while you're deciding that, what are the subdivisions? In this case, we had a graph with like, let's see, 1, 2, 3, 4, 5, major, and then minor. This subdivisions. The best thing to do, if you can, is to put 10 subdivisions between the major units. Like if you're going from 10 here and you're going through 20 here, then you get 10 subdivisions, and that each one of these would be equal to 1. It's easier to read it if you're thinking in decimal terms. And then, let's see. I forgot what the fifth one was. Let's see, here it is. Okay, I incorporated okay. No, this is unit dimensions. Excuse me. This is unit dimensions. Actually, that's 4. That's in 3, 3, 4, 5. Here we go. So the scale units and then unit dimensions. Are required. Then use the maximum available space. And then look at your subdivisions. Those are the 5 key items that you have to, when you're drawing one by hand. Okay. Interpolating, extrapolating, we talked about that. Direct proportion. Y equals mx plus b. Sound familiar? Straight line? Yep. And once you've drawn your best fit line, you can calculate the slope. If the line falls on actual data points, that's great. You can use those. But if it doesn't, right? If it just makes the best fit line for all your points and none of them fall on the line, you can just pick 2 points on that line and calculate your slope. Right? Because you're not calculating the slope of the data points, you're calculating the slope of the line. All right. Nonlinear relationships. All right. Here, our example is pressure versus volume of a confined gas. That's Boyle's law. So what is the experimenter changing? Changing the pressure. We change the pressure on the confined gas. What effect does it have on its volume? So as we increase the pressure, we get a decrease in volume. That's an inverse relationship. And this is a curve. In fact, it's represented by pressure times volume equals a constant. That's Boyle's law. And anytime you get a product of two variables equals a constant, you're going to have a shape of a curve like that. It's going to be a hyperbola. Because if it's going to be constant, when this one goes up, that one has to go down. Now, volume and temperature is a direct relationship. Right? When the temperature goes up, the volume has to go up to make that constant. Okay? But that gives us a straight line. Whereas this one gives us a curve. And scientists hate curves. We use them when we have to. We'd rather have a straight line. So very often we do some mathematical gymnastics to create a straight line out of the data that originally gave us a curve. And this is one good example. If we take pressure and volume like this and just plot them, we get that hyperbola. But let's do some math here. If I divide both sides of this equation by volume, that's permitted, correct? So I'll divide this side by V and this side by V. That one cancels V's. So now I'm just left with P, pressure on this side, and K over V on that side. Well, I don't like the way that looks. I'm going to say K is in the numerator, so I'm going to keep it there. And this is 1 over V. Right? Okay? So this is my Y. This is my slope. This is my X. With a Y-intercept of 0. It goes through the origin. So that's why it's not there. We don't have the Y-intercept. Well, we do, but it's just not in the equation. So if I plot, instead of pressure times volume, I still put pressure down here because I'm the one controlling it. This is the X, the independent variable. But now the dependent variable is 1 over V. Now I'm going to get a straight line with a slope of K. Okay? So what are the units? Well, let's see. Originally, the units were atmospheres for pressure. Got to have atmospheres. I didn't put the title in here, but you put the title. Then we put our data points in our best fit curve. And 1 over V now, what are the units of measure? Remember, when you do something to the variable, you also do it to the unit. So the unit of measure here is liters to the -1. It's inverse liters is the unit of measure. So now, if I want to find out what volume at what pressure, I don't need a difficult to draw curve on my points. And it can be done. Use a French curve. You ever seen a French curve? Yeah, it's a piece of plastic with a decreasing radius. Or go this way, a decreasing radius. So you can fit it to your points, just move it around until it fits the best. But if we can do it like this, we got a straight line. So now I want to know if I've got points in here that give me this 1 over V. Suppose I want this position right here. At this pressure, what would the volume be? Well, that'll give me the inverse volume. It won't give me the volume. So how do I get the volume? Take the inverse of it. Just flip it back the way it came. Now you have the volume. So you can use the graph to find this value, but then you have to take the inverse of it to get the original data point. Okay. All right. And there are other possibilities here. This has a curve. And if we try to take the inverse of it, it doesn't give us a straight line. But if we take the common log of the value, we get a straight line. All right, other applications. Okay, now we're getting into territory where this discussion is going to be applicable for the bonus questions. Right? We got two sections in here. The required section, we stop at where we've come so far. We stop with the volume temperature relationship, pressure volume relationship, plus the pressure inverse volume relationship. So you got three graphs to draw. And then when we get into this, I made this bonus because this is a little deep for now. We haven't gotten to these things, but if you want to tackle it, that's up to you. So you got questions in there that if you plot this titration curve, volume of base added to, relative to pH, you're going to get a sigmoid curve. And then another set of data, you get a broken curve. So take it or leave it. You can do it if you feel like it. And that's where the required section starts. There, 78 points. Bonus is possible 39 points. Some of my students do these, and rather than try to draw the graph, they see if they can look at the data and get the answers from the data alone for the questions that appear in the bonus section. So if we go down to the bonus section here, they might look at the data and say, okay, some of these you can answer without plotting it. So you can get a few extra points without going through the pain of trying to draw the graph. Okay,